friends, this is lecture number 58 on irrigation performance evaluation. So, in the previous lecture, up to previous lecture, we have completed the drainage part. So, the next 3 lectures we are going to see the irrigation performance evaluation. In the next lecture, it will be irrigation economics, and in the last lecture, so we will be going to run irrigation model CropVat, and so that is it. So, we are going to finish wrap up very soon in the following 3 lectures. Okay. So, in this lecture mostly we will be talking about irrigation performance evaluation. So, the water loss generally may happen through spray droplets in case of sprinkler irrigation, bead water use, soil evaporation, furrow evaporation, leaks in pipes, seepage and evaporation from irrigation ditches, surface runoff and depercolation. So, the amount of water you apply in the field can be lost in different ways. So, one in case of sprinkler irrigation, so the droplets can evaporate, so that is a loss, and in case of surface irrigation or any other irrigations, so the weed growth is commonly seen. So, that also requires some water, and soil evaporation, furrow evaporation, so leaks in pipelines, all these losses, if you include the amount of water you are giving, it is not really utilized by the plant. Okay. So, there is a lot of loss. So, sometimes this causes the inadequacy. Irrigation application results in crop water stress and yield reduction. This is due to inadequacy of water, and sometimes you excess the water. Irrigation application can be excess. So, that results in pollution of water resources because of the excess water can cause the runoff, and the runoff may leave the fields and carry a lot of pollutants and pollute the surrounding water bodies. So, the efficient use of irrigation water, so generally maximizes the economic return and water resources sustainability. So, this is what we are expecting from efficient use of water, irrigation water. So, first thing is to get an economic returns, and the other one is the water resources are sustainable, are going to be sustainable. So, we have to see whether the irrigation water we are giving is really performing, the irrigation system is performing well in delivering this irrigation water, and leading to economic returns and also the sustainability of water resources. So, basically the benefits of irrigation water, the beneficial use are 2 types. There is a crop evapotranspiration requirement, and then leaching of salts from the soil. So, these 2 are the beneficial use of the crop production. So, the first one is to grow the crop, the other one is to remove the salts from the root zone, so that it will not cause any stress, osmotic stress on the plants. And then non-beneficial use of irrigation water, like evaporation from water and soil surface. So, sometimes, these are also when you apply in the field, so still the water is lying on the ground, so that may evaporate and also the soil surface, which does not contribute to crop productivity. Okay. So, that is a non-beneficial use. So, irrigation efficiency defined from 3 point of view. So, the one is irrigation system performance, and the second is uniformity of water application, and third, response of the crop to irrigation. So, we are going to see the different indicators in following these 3 the points. The one is irrigation system performance. So, in order to understand how the system is performing for a given irrigation water. So, then the uniformity of water application. So, when the system is delivered to the water, whether that is really uniformly applied in the field or not. And the third is the amount you given to the field is really taken up the plant beneficially or not. So, in these three cases we are going to see the indicators to understand the performance of irrigation water. Okay, irrigation efficiency is the first one. So, this evaluating the irrigation system performance. So, basically the indicators are 6 and even more in some other cases. So, the mostly like first one is the water conveyance efficiency. So, that from the canal to the field water, I mean agricultural fields, the amount of water which you are delivering from canal and giving to the field. So, that may not be same. So, there is efficiency term. So, the system definitely have some efficiency issues. So, that is the water conveyance efficiency, and then second is the water application efficiency. So, the moment you received water from the canals at the field level, and then you will be using the irrigation system to deliver to the field. So, then the on-farm irrigation systems like sprinklers and furrows, they may not be having 100% efficient. So, there we are going to see the application efficiency, and then water storage efficiency. The water which is applied to the field should be stored in the root zone and then beneficially used by the plants. So, then whether the amount which are applied to the field is being stored in the root zone efficiently or not, that storage efficiency. Then irrigation efficiency, the overall irrigation efficiency, and then effective irrigation efficiency. We are going to see all these indicators in the coming slides. Okay. So, let us see, the first one is water conveyance efficiency. So, the water conveyance efficiency, as I said, it is the water delivered to the farm or field is usually less than the water delivered from the source, that is canals, for example. So, due to canal seepage loss, canal spills, evaporation losses from the canals, and that leaks in pipelines. So, it is expressed as Vf minus Vt. So, since it is a fraction, if you can multiply with 100, you get Ec in percentage. So, that is Vf is the volume of irrigation water that reaches to the field or farm, and Vt is the volume of irrigation water diverted from the water source. So, that is from the canal. So, the units could be acre inch or hectare centimeter or hectare millimeters. Okay. So, that is Ec. So, typically the conveyance losses are much lower for pipelines, because that is due to less the leakages, reduced evaporation and seepage losses. Okay. So, now and the next one is water application efficiency. So, this is very important as for the on-farm water management is concerned. So, the objective is to apply the water and store it in the crop root zone to meet the crop water requirement. So, Vf is Vf is the amount of water delivered to the field, and Vs is the volume of water stored in the root zone. For example, here in this case, so there is a furrow irrigated field, right. So, so the black one is, this one is moisture stored in the root zone, right, and then there is a still wetting front. Okay. So, this is what we do not require for the crop, because this is in excess of the crop root zone, and this is called excess water or depercolation. And if you see this spot, this is a dry spot which did not receive any water. So, there is a dry spot. So, you can clearly see the there is a deficit, and there is a sufficient here. So, this is upstream and downstream, and so water is moving from upstream to downstream, and this is the soil moisture. So, in this case, the amount of water you apply to the field is going away from the root zone in most of the cases, and there is deficit also. So, that means, so our objective is to fill the root zone exactly what it requires. Okay. And since you have the excess and there is a deficit, So, this is not uniform and efficiency may not be 100%. So, that is the reason Vs is the volume of irrigation water stored in the root zone, and Vf is the volume of irrigation water delivered to the farm field. So, generally in case of water loss from sprinkler system, so that is due to wind drift and evaporation from the droplets in the air and crop canopy and soils, these are the losses, whereas in surface irrigation the water may lose or loss through runoff, evaporation or furrow channels and surface runoff percolation. So, this may happen. So, that is the reason the amount you applied in the field may not be 100% efficient in storing the root zone. Okay. So, the next is, so here there is a table showing the potential application efficiencies for well designed and well managed irrigation systems. For example, sprinkler irrigation, this is a low energy precision applicator, it has 80 to 90% and linear move sprinklers 75 to 85%, central pivot 75 to 85% and solid set 70 to 85%. Whereas in surface irrigation you can see furrow irrigation, so compared to sprinkler irrigation is less efficient and 45 to 65 furrow is a conventional, and tailwater reuse a little bit higher efficient, and basin precision level basins. So, these are all little higher efficiency compared to other surface irrigation systems. And the micro irrigation systems can go up to more than 95% in case of subsurface drip irrigations. Okay. So, these are application efficiencies, this overall view, and the next is a third indicator. So, that is a soil water sorry. So, that is a soil water storage efficiency. So, this indicates how well the system uses the available root zone storage capacity to store water to meet crop needs. Okay. So, here you have the storage, right, you have the storage of root zone, right. So, you have that Vs is that is the storage, but how efficiently this stored water is being utilized by the plant. So, here numerator, this is the Vs is the stored water, whereas Vfc minus Va, so Vfc is the volume of water at field capacity and Va is the volume of water in the root zone prior to an irrigation event. Okay. So, that means, so here this much volume of water is being used by the crop or by the crop during the last irrigation event, okay, during the or the previous irrigation event. So, this is the volume of water stored, and this is the effectively the volume of water being used. So, we are not completely tapping the 100% of soil water, right. So, the part of water is being used for crop production or the evapotranspiration load. Okay. So, this way the soil water storage efficiency is defined, and refilling the soil water storage about 90% of the field capacity can be a good strategy. So, this is a deficit irrigation strategy. So, the mostly 90% is a good strategy, but generally I mean we can still go up to 60% MEID, so manageable allowable deficit. So, sprinkler and micro irrigation systems usually supply only sufficient water to satisfy crop ET. It is not like the surface irrigation systems, you can go for some kind of deficit. Okay. So, and then fourth indicator here is the irrigation efficiency, that is EI. So, irrigation water may be applied for other beneficial uses, for example, removal of salts, that is a leachate fraction, and microclimate control. Suppose the soil is frosted, if you can supply water that may warm up the soil, then and the frost can be defrosted. So, seed bed preparation, germination of seeds, softening of soil crust, and chemigation. So, right. So, chemigation is, that means fertigation kind of thing. So, all these activities require water. So, So, these when more than ET water used is considered, only beneficial care is considered in EI. Okay. So, in this VB by VF, so VF is the amount of water applied to the field, volume of water, and then VB is the volume of water beneficially used. So, you apply lot of water, but the thing is, so what beneficially, the crop is being used for beneficial purpose in order to grow the crop. For example, removal of salts, that is the beneficial, right, and then microclimate control. So, this is all used for creating a favorable environment to the crop production. So, we need to consider this water, and that is VB, right, by VF by 100. Okay. And then next is the fifth one is overall irrigation efficiency, EO. So, that is conveyance efficiency and multiplied by application efficiency. So, water conveyance efficiency in fraction, application efficiency in fraction, if you can multiply that, you get the overall irrigation efficiency. And then sixth one is effective irrigation efficiency. So, what happened, sometimes you the runoff which is been generated from the field can be reused, right. So, in that case you are again using the runoff water, I mean recirculating as irrigation water. So, then the irrigation efficiency may improve. So, in that case the irrigation, this is called effective irrigation efficiency. So, this is overall irrigation efficiency, and then this is FR, fraction of the runoff water which is being used as irrigation water. So, that is fraction, and 1 minus E naught, right, into 100. So, this the fraction of surface runoff or seepage or deep percolation that is recovered from the field. So, that can be used as irrigation, that is the fraction. So, this way the effective irrigation efficiency is being estimated. So, now irrigation. So, the second one is the irrigation uniformity. So, the whatever we discussed, that is all efficiencies, and the second the case or second performance indicator is the irrigation uniformity. So, here non-uniformity in surface irrigation, basically that is caused because of differences in opportunity time of infiltration. Suppose you have a field here. So, here infiltration is more, infiltration is less, maybe infiltration is more. So, this definitely causes this non-uniformity in a soil root zone. Okay. So, that is one case, and spatial variability of soil infiltration properties, as I said, if that is definitely I mean different amount of infiltration depth caused by the infiltration properties of the soil, and non-uniform grades. So, so the grade is not uniform. So, definitely here there is a depression and more infiltration is taking place. So, like that it's right. So, definitely that is also causing the non-uniformity, and non-uniformity in micro irrigation. So, this is basically variations in pressure caused by pipe friction and topography, and variations in hydraulic properties of emitters or emission points, and soil wetting from emission points. Okay. So, these are definitely going to cause this non-uniformity in micro irrigation, and generally irrigation uniformity is calculated based on the indirect measurements such as so the first one is Christiansen's uniformity coefficient. So, that is mentioned as Cu for sprinkler irrigation mostly. So, if you see in case of sprinklers, so these are the sprinklers, for example, in this figure. So, the catch cans are arranged in a known grid intervals, right, known grid intervals, and then we are going to collect water for a specific period of time, and then after that we are going to see whether the sprinkler irrigation system is uniform, I mean irrigation is uniform distributed or not. Okay. So, if you see, this is the equation is being used to estimate Cu, that is Christiansen's uniformity coefficient. So, 1 minus x I minus x m by sigma x I into 100. So, that is x I is the depth of water which is measured in each catch can, and this is the average depth of all catch cans, and then divided by the sigma height, the total amount of water, I mean the depth of the total catch cans. Okay, so that is sigma x I. So x I is measured depth of water equally except the mean depth of water in the catch cans. Okay. So this way you can calculate Cu, and then the next is the second indicator in case of irrigation uniformity is low quarter distribution uniformity. This is basically applicable for surface irrigation systems. So if you see this is the head end and this is the tail end of furrow irrigated field or border irrigation field. So water is flowing from head end to tail end, and this is the water depth which is been observed at the head end, which is because a lot of water will be available here, and then lowest, I mean minimum water depth will be available at the tail end. Okay. So if this is the required water, I mean this is the required desired root zone depth. So this one, if you see the deficit, okay, and beneficial, this is a dP, okay, and what is used for satisfying a SMD soil moisture deficit. Okay. So here du is generally estimated as the depth of the wetting front at the lower quarter divided by average depth of the water, I mean infiltrated water in the field, I mean throughout the field into 100. Okay. So that means if suppose this is 1/4 of the field, so this is lower quarter depth. So this is lower quarter depth d LQ minus average, so the DAV. So that divided by I mean DAV into 100. Okay. So du generally less than 60% non-uniform, and du greater than equal to 60% is uniform. Okay. So depth of water infiltrated in the lower 1/4 of the field. So that means here, so this one is DLQ and this one is DAV. Okay. So not this one. So this is the lower quarter and this is the average. Okay. So then irrigation uniformity, this is third one. So that is emission uniformity for micro irrigation systems. So in case of micro irrigation systems, and this is not directly, which is I mean it's not wetting the field completely in case of sprinkler and surface irrigation systems, because if this is a dripper, so there is a wetting spot here, there is a wetting spot here, and it goes like this. So there are patches of wetting, wetting patches are seen in case of drip irrigation system. So definitely the uniformity is estimated or different. Okay. So here Cu and Du concepts are impractical for micro irrigation. So that is why here EU is introduced, that is emission uniformity, right, which is a given equation like 1 minus 1.27 into CVM, which is manufacturer's coefficient of uniformity, right, into N. So N is the number of emitters per plant. Okay. So then Q min by Q average. So Q min is the minimum emitter discharge rate at a minimum system pressure, at a minimum system pressure. Okay. And Q average is average emitter discharge, that is GPM. So this is average emitter discharge, and Q minimum is the minimum of all emitter discharges. Suppose you have a emitter here, and there is second emitter, third emitter, fourth emitter, number of emitters. So Q average is the average, I mean you can collect the discharge from each and every emitter point. Okay. So then you are going to average the flow rate and Q min, find out the Q min of among all the catch cans. Okay. So that will be the Q min and Q average, and CV, this is the manufacturer's coefficient of uniformity for the particular emitter type, and you can calculate the emission uniformity. Okay, so then the fourth one is coefficient of design uniformity, the CUD. So, design uniformity, so there is 1 minus 0.798 into manufacturer's coefficient of uniformity and number of emitters into 100. So, this will give the coefficient of design uniformity. Okay. So, then the third one is crop response to irrigation. So, the first one is irrigation efficiencies, and second is uniformity, and third is the amount of water you give, whether how the crop is responding to the water you apply to the field. So, here the irrigation system performance and irrigation uniformity parameter discussed previously evaluate the engineering operation aspects of the irrigation system. So, here the three most commonly used parameters in case of crop response to irrigation are crop water use efficiency, irrigation water use efficiency and water use efficiency. Okay, so, these efficiency we are going to see. The first one is crop water use efficiency, CWE, crop water use efficiency, that is yield difference divided by evapotranspiration differences in case of irrigated field and rain fed field. So, yi is the yield obtained in case of irrigated field and yd is obtained yield in case of rain fed field, and similarly ETI is the evapotranspiration observed in case of irrigated condition and in rain fed condition. So, this will give the crop water use efficiency. So, here in case of generally the crop if you grow, so we do not know how much is irrigation water and how much is the rainfall. I mean the crop response due to irrigation, crop response due to rainfall is not being separated, cannot be separated, right. So, that is why you need to experiment separately and then find out the crop water use efficiency. So, this will give the irrigation response to crop yield. Okay. And then, so the next one is the irrigation water use efficiency. So, this is, so similarly yi is the yield due to irrigation, yield due to rain fed, and IR is the irrigation water. So, depth of irrigation water applied in the irrigation, which does not account for irrigation application losses. So, we generally use for beneficial beneficially used irrigation water. Okay. And then water use efficiency. So, this in this water use efficiency, this is the yield due to irrigation, and then so this is entire water we applied. Generally one is for this is effective precipitation or effective rainfall and irrigation water applied and the soil moisture which is present in the soil. So, this much water you have applied to the field and then as a result you receive this yield. So, this is water use efficiency. Okay. So, in this we are including that the entire water we apply to the field, including the beneficial, non beneficial all. Okay. So, here then example, a stream of 150 liter per second was delivered from a canal and 110 liter per second were delivered to the field. Okay. So, an area of 2.2 hectare was irrigated in 8 hours. So, here is 2.2 hectares and this is for irrigated for 8 hours and there is a canal, from canal the water is being so at this point, so water is 150 LPS, whereas at the field level, so it is measured as 110 LPS. Okay. And so, now the effective root zone here is 1.5 meter and the runoff losses in the field was 445 cubic meter. So, this is 445 meter cube is the runoff from the field. So, the depth of water penetration varied linearly from 1.5 meter at the head end. So, suppose this is the head end and this is the tail end. So, this here is 1.5 meter whereas here you get 1.1 meter the infiltration depth. Okay. So, that is the variation within the soil root zone, and available moisture holding capacity in soil is 200 mm per meter depth of soil. Determine the water conveyance efficiency, water application efficiency, water storage efficiency and water distribution efficiency. Okay. Irrigation was started at a moisture extraction level of 50%. So, 50% when the moisture depletes 50% from the field capacity, you are going to irrigate. So, with these conditions, so find out the efficiencies. So, the first is water conveyance efficiency. So, this is straightforward, that is amount of water being diverted from the canal and received at the field end. So, here 110, 150 from the canal and 110 at the field level. So, it gives 73.33% is the conveyance efficiency. So, next is the application efficiency. So, water application efficiency, the formula is volume of water stored in the root zone applied in the field level. So, water delivered to the plot, so the 110 at the field level, right, and this is this is irrigated for 8 hours. Okay. So, and then 8 hours is being converted into seconds, 60 into 60, right. So, and 110 liters, 110 liter per second, right. So, then this hours is converted into seconds. So, liter per second and now seconds, this gets cancels out, and liters. So, liters converting to meter cube is divided by 1000. So, that will be 3168 meter cube of water is being delivered to the field if we irrigate for 8 hours. Okay. So, this one, and runoff is given 445 meter cube. So, Vs, which is really effective, right, that is this minus this, that is 27 to 23 is the volume of water stored in the root zone. So, this is 2723 and 3168 is applied. So, that will be 86% is the application efficiency. Okay. And then next is the water storage efficiency. So, water storage efficiency, that is Vs is the volume of water which is stored in the root zone, and then Vfc the volume of water field capacity, and Va is the volume of water exactly just prior to the next irrigation. So, Vfc is 200 into 1.5 because 200 mm per meter depth is the moisture availability. So, moisture holding capacity. So, that is 200 into 1.5 is the root zone depth, that will be 300 mm is the water holding capacity in the root zone. And Va, so it said like 50% is when it gets 50% of Vfc is depleted, then irrigation is going to start. So, 50% is of 300 mm, that is 150 mm. So, if the amount of water, the availability of water is 150 mm and we start irrigation. So, Vfc minus Va, that is 150 mm because this minus this 150. So, then for the entire field, if you see this is 2.2 hectares, okay, and 150 mm is the available water. So, this is meter cube, conversion of meter cube, hectares to meter cube, and divided by 1000 will give the, so this is mm. So, mm convert to meters divided by 1000. So, that is 3300 meter cube is the Vfc minus Va. Now, Es is equal to 2723 and Vfc minus Va, that is 82.52% is the water storage efficiency. So, and next is your water distribution efficiency. So, if you see if in the problem it is given, so water distribution is taking place like 1.5 at the head end and tail end. So, this is up to 1.1 meters, right. So, this is the wetting front profile at the end of the irrigation. So, now depth of water stored in the root zone, that is D. the average depth will be 1.3 meters, and numerical deviation from the penetration. So, at the end of the field, so here so numerical deviation would be, so you x I minus x bar, right. So, that will be 1.5 minus 1.3 0.2, and tail end 1.3 minus 1.1 0.2. So, now average numerical deviation, right. So, that will be 0.2 plus 0.2 divided by 2, this will be 0.2. Okay. Now, distribution uniformity is equal to 1 minus y by d into 100. So, that is 0.2 divided by 1.3 equal 84.62. Okay. So, this is similar to your Christianson's uniformity distribution, which is sigma x I minus x bar divided by sigma x I. Okay. So, this is similar to that. Okay. Okay, so, with this we conclude this lecture. So, in this basically the irrigation system performance is being understood by basically the three cases. So, the first one is the efficiencies, system efficiencies, and second is uniformity, and third one is response irrigation response to yield. Okay. So, or yield response to irrigation water we applied. Okay. So, with this basically whether the system is working efficiently or not, and then are we getting the economic yield or not. So, all these things will be carried out based on the understanding how we understood the application efficiencies, okay, and then the distributions, okay, and then crop water crop water efficiencies, and irrigation efficiencies, and water use efficiencies, all these things. Okay. Yeah. So, the next lecture we are going to talk about the irrigation economics. Okay. Yeah. Thank you.